Welcome to the fifth lecture of this lecture series. In this video, I am going to discuss about the resolving power, Rayleigh criteria of resolution, and the resolving power of a diffraction grating. Before starting this video, I would request you to please watch the previous videos on this lecture series, especially the lecture 4, which covered the diffraction pattern due to grating, because you will need some of the information from the previous videos. Okay, so let's start Rayleigh criteria of resolution. So before discussing this criteria, the first questions come in the mind is what is resolving power of an optical instrument. So resolving power of an optical instrument is nothing but its ability to distinguish, or you can say resolve, a small or closely adjacent images or object. Okay, like if you are placing two objects very nearby in front of an optical instrument, whether you are able to resolve it or not. Okay, the very common example of you can understand of this resolving power, like our common eye, we easily distinguish bigger objects which are in front of us, that we can clearly distinguish between two objects. But if you look very far in the sky, the angular separation between two stars sometimes very small. So sometimes if you look and you will think whether it's a single star, but actually if you watch that star from a high resolution telescope, you will find out from your naked eye you are thinking this is only a single star, but from the telescope you will able to know that is not the single star, there are the cluster of stars. Okay, so that's how we can think about this resolving. Now Rayleigh gives some criteria to know whether some optical instrument is able to resolve it or not, based upon the diffraction pattern formed by those object or source. Okay, now what it say that two nearby point source could be just resolved, okay, if the distance between them such. Okay, so what it means, it's giving us limitation on the distance between the two objects. So it pointing out if the distance between them is less than some limiting quantity, then we will not able to resolve. And what's the limit? That limit is explained by this, such that the central maxima in the diffraction pattern of one source coincide with the first minima in the diffraction pattern of the other source. Means if two objects forming the diffraction pattern, and if you consider the diffraction pattern of one object and just point out the central maxima of that diffraction pattern, and if that central maxima is coincide or far away, okay, from the, or the limiting point is when the central maxima is exactly coincide with the first minima in the pattern of the other. Okay, now you can understand this clearly by looking graphically. Okay, just look at here. Suppose this is the diffraction pattern formed by the first object. Okay, and then this is the diffraction pattern formed by the another object. Now according to Rayleigh criteria, this central maxima must coincide with this minimum, but it is less than that. So it is not satisfying the Rayleigh criteria, and then the things come in our mind that these two objects is not resolved by that particular optical instrument. Now, in other words, the angular separation, if you think in terms of angle, okay, then the angular separation between these two principal maxima must be half of the total angular width of principal maxima. So this is the principal maximum, and then what is the angular width is this to this, okay, and half of this width is this much. So the angular separation between these two must be equal or more than the half of angular width. But here this is not the case, and if this is not the case, then what we will see is this. This is the resultant pattern. So in the resultant pattern, we will see only single peak, and that's indicate only one object. So if the distance between them is such that they are forming this kind of pattern, then optical instrument is not able to say whether there is a two. He will always point out, it will always point out that there is only single object. So this is not able to resolve. Now in another case, suppose the distance between such that this is the diffraction pattern of one object and this is the diffraction pattern of another object. Now here you can look that the principal maxima of second one is coinciding with the first minima of the first diffraction pattern. Now from the Rayleigh criteria, it's satisfying that criteria. That means the optical instrument able to resolve these two objects. Okay? And this is what the resultant pattern will look like. It will have a dip here. Okay, it will have a dip, and now if you look on this resultant pattern, you can easily find out two maxima. Okay, and a dip, so it indicating two objects. These two distances is exactly equal. That is the angular separation between these two is half of the angular separation of this principal maximum. Now just come to our next topic, resolving power of a grating. Anyway, if you don't understand this point clearly, you can just leave a comment on the comment section. So now, resolving power of a grating. Now, grating we generally use to find out the wavelength of light. Okay, so it is just suppose in some case you have a light such that they are consist of a band of wavelength and two wavelengths are very nearby. So whether we will able to detect those two or not, that depend upon the resolving power of grating. And so it is an ability to distinguish between two spectral closed line. Okay, and it is given by lambda by d lambda. So if you know this quantity, you can know the resolving power of a grating. Okay, so if your line, if your wavelength is very nearby, you can use high resolving power grating in order to resolve. Okay, here d theta, d lambda, sorry, is the difference between the wavelength. Now to calculate this quantity, we will just draw a small schematic. So suppose we have a plane grating on which the lights coming from two sources is falling, okay, and forming a diffraction pattern. Suppose this is the diffraction pattern formed by the first object, okay, first source, and we consider the wavelength of that source is lambda. This is the diffraction pattern due to second source and having the wavelength lambda plus d lambda. Okay, so and we are considering the mth order principal maxima or pth order. Okay, you can say anything, but not the central maxima, because central maxima is same for any wavelength of light. Okay, central diffraction maxima. Remember this point, central diffraction mean maxima, because central diffraction maxima is independent of wavelength of light. So we are considering the mth order principal maxima. Okay, so this is the mth order principal maxima of wavelength lambda. This is the mth order principal maxima of wavelength lambda plus d lambda, and we considering here that both are satisfying the Rayleigh criteria, because we need to resolve this quantity. That's why the mth order principal maxima of lambda plus d lambda is coinciding with the first minima after the mth order principal maxima of wavelength lambda. And this is the angle of diffraction for the principal maxima, and this is the angle of diffraction for the first order minimum. These are the two quantity of grating. Property of structural property of grating, that is grating element, is a plus b. A is this this slit width, and b is the opaque space. N is the number of slits present in that grating. Okay. Now, in order to calculate lambda plus d lambda, we need some information from our previous video, like the condition for the pth order principal maxima. So what is the pth order principal maxima condition? If you watch the previous video, you can easily guess it is a plus b sine theta equals to p lambda. Remember, it's a interference maximum, principal interference maximum. A plus b sine theta equals to p lambda. Now we can differentiate this equation. So what we will have in this equation 2, d theta equals to p d lambda divided by a plus b cos theta. This d theta is nothing but the angular separation between two principal maxima of pth order. Like suppose your first source is making a principal maxima at angle theta, and second source is making pth order principal maxima at theta plus d. So this d theta is the angular separation between these two principal maxima. Okay. Now just rewrite equation 1. Remember, this equation we need later on. So just rewrite equation 1. Multiply number of by n. N is the number of slits. Now if you just write it separately, like if you write the condition for the 0th order principal maxima, first order principal maxima, second order principal maxima, and so on, then you can substitute the value of p by 0, 1, 2, and we will have this equation 3. Okay, so this is the condition for the 0th order principal maxima. This is the condition for the first order principal maxima. This is the condition for the second order, and so on. Now write the condition for the minima. Okay, so in general, for any order of secondary minima, we can write n a plus b sine theta equals to s lambda, where s have an integer value except 0, n, 2n, 3n, and so on, because for s equals to 0, n, 2n, that will exactly the condition of principal maxima. so we need to discard those terms. So this is, so if you want to write the first order minima, you need to just place s equals to 1. If you want to write second order minima, you write s equals to 2, and so on. Now just extend this equation. So this is the first order minima, second order minima, dot 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 dot. Now this is, and here you see the n lambda is missing, because when you reach n lambda, that is the condition for principal maxima. Okay, first order principal maxima. So this is zeroth order principal maxima, then these are the minima, and then here arrives the first order principal maxima, and so on. So if you compare this equation with the condition for the maxima, you will find out the first minima just after the principal maxima having a distance difference of lambda. Like this is the zeroth order principal maxima. Okay, then first order minima having lambda here. This is the condition for first order maxima, and this is the condition for the first minima just after first order maxima. So you can see easily there is a difference of distance lambda. Okay, so this is, remember that point. Now we know the angle of diffraction for the first minima is theta plus d theta after principal maxima. We can just revisit that schematic. So suppose this is the any order of principal maxima having angle theta, then first minima just after the principal maxima having angle theta plus d theta. So we can use these two concepts to write the condition only for the first minima. Okay, so the condition for the first minima will be n a plus b sine theta plus d theta. Now the angle of diffraction given theta plus d theta equals to np lambda. This is the condition for the pth order principal maxima plus lambda. Okay, so remember this is in general condition for the minima of any order, and this is the particular condition for only first minima just after principal maxima. Okay, so now from equation 1 we know this condition. Okay, so we know this, we have equation 1, we have equation 5. So just divide equation 5 by equation 1. What we will have is this equation. Okay, now we can use sin a plus b equals to sin a cos b cos a sin b formula to expanding this term. So we can write this. Here we have assumed d theta is very small, so cos d theta equals to 1 and sin d theta will be approximately equals to d theta. So we can write this. Simplify this again, we will have d theta equals to 1 by np cot theta. Now we have already obtained this d theta by another method, like in equation 2. So we can compare this equation 2 with equation 6, and what we will have is this equation. Further simplify this by substituting a plus b sin theta equals to p lambda. Finally we get what we are wanting, lambda by d lambda equals to np. Now here we can note for a particular order, resolving power of a grating is proportional to number of slit. Okay, so just remember this formula is very important. If you want to rewrite this formula in another form, then you just use this identity a plus b sine theta equals to p lambda, you will have this, and if the total width of slit is w, which you can obtain by n into a plus b, then we will have another form of resolving power. This is lambda by d lambda equals to w sine theta lambda. So now if you just discarding the order number, so if you want to know the resolving power as a function of lambda, so for a particular lambda, resolving power is proportional to width. Okay, so if your lambda is small, then your resolving power is decreased, so you have to increase more width in order to compensate that. So the resolving power for a particular wavelength lambda is proportional to width of the slit, and in that case it's independent of number of slits. What the maximum resolving power you can achieve, that you can obtain by substituting sine theta equals to 1, because sine theta is maximum value of sine theta is 1, then max lambda by d lambda is nothing but w by lambda. So remember, these formulas are very important. It will help you to solve some of the problem on the resolving power of a grating. So in this lecture we are stopping here. See you in next part. Thank you.